Welcome back to lab this week. We're going to be talking about the results section. Finally, we've been talking about a lot of how to analyze, how to do your correlations and t-tests, but now we're going to talk about how to write it up. So a results section has three general sections. The first is a summary of what data you collected. The second is the details about the statistical tests that you used to do those hypotheses, to test those hypotheses. And then the third is the actual results of the analysis. A lot of what we've talked about the past couple of weeks with correlation and t-test has been this third point, the actual results and how to write up those statistics. But we do want to touch on the first 2 points today. It's very important to note that the implications of your research, the validity issues that we're talking about, are not discussed in the results section. Those are instead going to be discussed in your discussion section. The first part of the results section is to include a summary of the data you collected. That just means all of the descriptive statistics for the variables that you're using in your analyses. So what did your sample actually score on these? Now, a lot of this might overlap with stuff that was in the methods section, and so you don't need to include necessarily redundant information, though sometimes it is useful to have the data reiterated in your results section. Anything that you didn't include in your methods that is describing the variables that you used should now go in the results section. But again, I sometimes find it very useful to just reiterate the different descriptive statistics in both sections, with the idea being that sometimes people don't read through an article going introduction, methods, results, discussion. Sometimes they might just jump straight to the results section, in which case I want to have that information available for the reader so that they understand. If you're doing a categorical variable, this just means including all the proportions of demographic factors and or your t-test variable, those groups that you're comparing to each other. For instance, you might have that describing your participation as 36 participants or 30% self-reported as non-smokers, whereas 84 participants or 70% were smokers. Here you have both the count of the proportion as well as the percentage proportion there. So for this, you're going to use a frequency analysis here because you're counting the number of times how frequently people fell into each group or condition. For continuous variables, you need to include the means and standard deviations of the scale. Again, this might be very similar to stuff that you included in your methods section, but you can consider incorporating that into your results section as well, and I highly encourage it. So you might have a sentence, the average score on the college stress scale was 4.8 with a standard deviation of 1.2. Now that's made up data, don't cite that in your own article, I just typed in some numbers. So you'll have to actually look up what the average college stress scale scores were for yourself. As a note, you only have to record and report descriptives for the variables you are using. Do not go over and above and try to report all of the variables that were on the survey. You just don't need it. You can also include any additional demographic variable breakdowns if you would like. In fact, you'll see on an article we're reading for Lab Assignment 3 that they have an entire table that describes all the demographic factors that they think are important associated with their data so that people can evaluate the external validity and even to a degree the internal validity of the study. Also, to reiterate, you don't have to include those frequency proportions for any categorical variables or t-test variables if they were addressed adequately in the participant section of the methods. So you don't necessarily need to reiterate, though I find it helpful. That being said, it is very useful to include the continuous variables to reiterate that in your methods section and your results section. So you can re-say what the average score on the college stress scale, for instance, was. It provides a lot of context. So you are going to be evaluated in your paper on how well you include this information and how well the reader can pick up on what these pieces of data, can find them and locate them in your paper. So it doesn't hurt to have it twice, but you are really the arbiter of that at the end of the day. As a quick reminder of how to run these analyses in SPSS, you can go for categorical variables to run frequency analyses with analyze, descriptive statistics, and then frequencies. You drag those variables or click them over to the variables box and click OK. If you're getting descriptives for your continuous variable, you need to do that descriptive analysis. Here you go, analyze, descriptive statistics, and then descriptives as the drop down. Put the variables in the variable box the same way, but this time click options and make sure that your mean, standard deviation, min and max are selected. That's the information that you need to report back. And then click OK. I'm not including any screenshots here because this is stuff we've gone over in previous labs, at least 2 different labs. So if you have any questions, go back to those labs, check it out. But by this point, you should be pretty familiar with how to run this and how to live within that Analyze drop-down tab. The next step is to set your significance. This just means telling the reader how are you going to evaluate that something was a significant effect, that what you found in your study actually reflects something interesting about the way the variables are related to each other. And this isn't always the same across studies. We have talked about the p is less than 0.05 as a standard accepted cutoff for what is significant. But this can change. You could maybe make it smaller, like a 0.01 is the cutoff. And so the probability of finding your data, assuming that there was nothing, there was a null effect in the real world, you can make sure that you only accept something as significant if that probability is really low, or you can make it higher. And so for us to understand why these numbers are different, we're going to take a little segue right now, take a little trail off of our normal discussion of results to talk a little bit about how we set these numbers. So a reminder when it comes to null hypothesis significance testing that we have 2 types of hypotheses. The first is the null hypothesis, which is the idea that the IV did not have an effect on the DV. There's no relationship between them. This is shown through a t-test that the means of the 2 levels of your IV are not significantly different from each other in terms of the dependent variable. With a correlation, it's just showing that the changes in the IV and the DV are not systematically related to each other. There is nothing interesting there, and this null hypothesis is represented by the HO. If the null hypothesis is not true, there's no effect, then logically you're left over with the fact that there is an effect, and that's called the alternative hypothesis. It's the alternative because it's what's left over if the null is incorrect. This is also referred to as the research hypothesis and represented by the symbol H1. So if there is an effect in a t-test, this would signify that the means are significantly different. The average dependent variable scores in both your groups are significantly different. Or in a correlation that the changes in the IV and the DV are systematically related to each other. As one shifts, the other shifts as well. So we have these 2 hypotheses. In null hypothesis significance testing, we are going to make a decision, one of 2 decisions as the researcher. And this is all based on what is the probability that the null is false. So if it's likely that the null is false, that the data that we got from our sample there's a strong effect there, so probably the null is wrong, that there is an effect somewhere. In that case, we're going to reject the null hypothesis and say that there are changes in the IV related to changes in the DV, that in a t-test the group means are significantly different. But if there's a low probability of the null hypothesis being false, and we can't find evidence that there's actually something interesting going on in the world, then we fail to reject the null hypothesis. We have to stick with it and say, well, I didn't find any evidence that it's wrong, so I guess we're going with it. We're not going to reject it. In this case, the changes in IV are not related to changes in DV, or we express this through a t-test as the group means are not significantly different. It is important to note here that we never accept the null. We just reject or fail to reject the null hypothesis. Similarly, we're never talking about the research hypothesis. We're not rejecting or accepting the research. It's all about how likely is it that we can reject the null hypothesis. Because we can never conclusively determine that there is or is not an effect. We are simply finding evidence leading us to think in one way or the other. So rejecting or failing to reject null. This decision-making process regarding the null hypothesis can be expressed in this 2x2 table. The rows you have here are about the truth of the null hypothesis. So in the real world, either there is an effect, in which case the null hypothesis is false, or there is no effect in the real world, in which case the null hypothesis is true. And then the two column options we have are what we gather from and what we decide from our study, either to reject the null hypothesis or to fail to reject the null hypothesis, to say there is an effect or to say, yeah, indeed, there is no effect. And you can see that the two options there, the two cells, have the correct decision. So if the null hypothesis indeed is false and there is an effect in the real world, and our study rejected the null hypothesis and said there is an effect in the real world, well, that is a correct decision. On the flip side, if the null hypothesis is true and there is no effect in the real world, then we're hoping that we fail to reject it, and we also agree from our study that there is no effect in the real world. That is, again, a correct decision. But you can see here there are two cells where that is just not the correct decision. If we make either of the other decisions, those are going to be error decisions, and we categorize them as type 1 and type 2. We did talk about these in a previous lecture, but I'm going to go into a little bit more detail on them now. So let's think about the guilty or not guilty analogy. So if we are in a courtroom and we're trying to figure out if somebody, the defendant, is guilty of something or not guilty, our null hypothesis would be that the person who's been arrested and is on trial is not guilty. They didn't do what we think they did. There's nothing interesting. They're just another person, an innocent individual. They didn't do it. Whereas the alternate or research hypothesis would be if the opposite of that, that if they are not guilty, then they are guilty. And that's actually how our legal system works. We assume that everybody is not guilty, and then through our trial procedure, we find evidence to suggest that they are guilty. These proven guilty beyond a reasonable doubt. So we assume innocence until proven guilty. Now, we are the prosecutors. We hope guilty. We hope to catch the criminals and remonstrate them for whatever they did. And in that case, we can kind of think about in this context of we're hoping to reject the null. We think that the person is guilty, but we have to assume they are not guilty until we find sufficient evidence beyond a reasonable doubt that they are in fact guilty. So this isn't a critique on the legal system, but this is the process that we use. We have to assume not guilty until we find enough evidence, and we do the same thing in research. We have to assume no effect until we find significant evidence, sufficient evidence, that there is an effect. So in a legal situation, if a jury returns a verdict of not guilty, it means that there is not sufficient evidence to find the suspect as guilty to support that alternative or research hypothesis. They fail to reject the null and suggest that the individual is innocent. All right, so this is the allegory, the analogy we're going to use. Guilty or not guilty, null hypothesis not guilty, research hypothesis they are guilty. So in this guilty or not guilty 2x2, we have the rows of the null hypothesis, which is that the suspect is not guilty. And if that is false, then the individual actually is guilty. And if it's true, the individual is not guilty. And then we as the jurors are coming to a conclusion. If we reject the null hypothesis, then we are presuming the individual is guilty. If we fail to reject the null hypothesis, then we are presuming not guilty. We're going along with that null hypothesis. You can see here that if we reject and presume guilty, and indeed the person is guilty, that's a correct decision. But if we fail to reject and we presume not guilty, and in fact the suspect is not guilty, that's also a correct decision. But if we do either of the others, we are committing an error. So the type 1 error is when we presume that the individual is guilty, but in fact they're not. So we're applying guilty when the person didn't do it. And the other option is that we say, oh no, they're innocent, when in fact they're guilty. Both of those are error. So that type 1, we're concluding that the means are different when they are not. That's what a type 1 is when we come to an experimental methods. We're concluding that there is something interesting in the real world when there is not. We conclude guilty when the person's actually innocent. And this is terrible because now there's an innocent person who's being remonstrated, is going to jail. The real criminal is still out on the street. That's really not good. So this type 1 error is made when we reject the null hypothesis, but the null is actually true. We interpret the results as due to an IV, that there is some effect, when actually any effects we did find are just random chance. Something about the sample we did, something about the maybe design confounds that were in our study that are not the actual IV. And this, we as researchers consider the worst of the worst. This is not what we want. We do not want to say we found something interesting between variables when there in fact is nothing interesting, because then we are associating two things that should not be associated, and we're missing the actual effect that might exist in the real world. The other option again is the type 2 error. This is when we conclude that the means are not different when they actually are. So we conclude not guilty when the person actually is guilty, and we let the criminal go free. This is an issue and an incorrect decision because we're failing to reject the null hypothesis even though there actually is an effect. The research hypothesis is true in the real world. So we are interpreting the results as due to random chance when actually it was our independent variable that was having the effect, but now we're not reporting it. We're saying the IV doesn't affect it, but it does. There's actually something interesting there that we failed to do. But we treat this as not as bad. It's still not good, but it's not as terrible as saying there's a relationship between two things. In general, we think of it as a greater injustice if we find someone guilty when they're not guilty, this innocent person going to jail, than if there's a criminal remaining on the streets. The idea being that someday down the road, the criminal will do something different. We'll test it in a different way, and then we'll find an effect. That a type 2 error says right now we didn't find an effect, but there's still reason that maybe down the road people will find an effect. But if we start telling a story of there being an effect between two variables, that somebody is guilty, that kind of creates a label, and people are going to reuse that information and say, well, this researcher found that these variables were related to each other, so I'm going to use that in my theory and move forward. When we establish that there is a relationship between two things, it's really hard to come back from. Whereas if you establish there's not a relationship, it's a lot easier for future researchers to say, you know what, I'm going to test that again and see, because I really do think there's a relationship between. I'm going to try it again. So type 2 can be a little bit easier. We can progress in science a little bit easier than if we make a type 1 error. That's why it's the worst of the worst. While type 1 is worse than a type 2, we still don't like either. We want to make just correct decisions. And so we would like an ideal world to eliminate both, only correct decisions, right? But that just can't be done. These type 1 and type 2 error influence each other. If we try to reduce our chances of getting a type 1 error, it actually inflates the other chance. It increases our likelihood of getting a type 2, and vice versa. If we decrease our chances of failing to reject the null when we should, it's going to inflate our chances of a type 1. So how does this work? You might remember our p-values. We've talked about it today, and we've talked about it a lot before. This p-value is the likelihood of finding effects in our data if there are no real effects in the real world. And we use a p cutoff, again, usually 0.05. This cutoff is set by what's known as an alpha level, and it's indicated by this Greek alpha, lowercase alpha there. It looks like a little italics A. And often we can set this at 0.05. This alpha level is the type 1 error rate. It's the likelihood of rejecting the null when we shouldn't reject the null hypothesis, of saying that there is something interesting when in fact there isn't anything interesting. That is our error rate. And so we say, okay, I need to set a point where I say, okay, I'm only going to accept significance if there's a less than 5% likelihood of getting a type 1 error. And we can decrease this alpha. We can change it to be even smaller, so a smaller likelihood of rejecting the null when we shouldn't, and make it harder. So now if we're using an alpha of 0.01 or a type 1 error rate of 0.01, then we need to find significance, or we can only find significance if p is less than 0.01. But as I started to say at the beginning of this slide, this increases the beta. which is a type 2 error rate. So type 2 error rate is associated with beta. It's a capital beta, the Greek letter, looks like a funny looking capital B. And so as we decrease our alpha, we're going to increase our beta. Then you can think of this as if you reduce your ability to reject the null, we're making it harder to reject the null when we shouldn't. So we just by necessity have to reject our ability or reduce our ability to reject the null. Then we're actually going to be increasing our likelihood of failing to reject the null when we should be rejecting the null, that type 2. So as you change your ability to reject the null, it's going to either increase or decrease our type 1 and type 2 error respectively. So when we are setting an alpha and thus affecting our p-value, this is very important for us to note and decide. We need to figure out, is 0.05 good? Is 0.1? How likely is it that I'm going to commit type 1 error? Am I really afraid of type 1 error in this? Do I really not want to get a wrong result that suggests there's a relationship? In which case I want to make a small alpha level of 0.01. But if I'm kind of okay, a little bit more like I'm just trying to see if there is some kind of maybe relationship between these two, it doesn't have to be very strong, but something there, well, then we're a little bit more okay with type 1, maybe we can increase. This is why researchers often just go with the happy medium of a 0.05. That's been found to be a pretty good balance between our type 1 and type 2 error. So most often you're going to find this in psychology. However, as you get into other sciences or into very specific investigations of variables related to each other, you'll often see the alpha levels get a lot smaller as people want to be very clear about the likelihood of rejecting that null when they shouldn't. So you'll see alpha levels of 0.01 or alpha levels of 0.001 even, less than 1 in 1,000 chance of rejecting the null when you should not. There's also a rule of thumb you might have learned in your statistics class that as you run multiple analyses, if you're doing a lot of analyses, it increases the chance of you getting a wrong result in one or more of those analyses. So you have to use a smaller a smaller alpha if you are running a lot of studies. But if you're just running one, you get a little bit more latitude and a little bit more flexibility. All right, so I know that was a lot to think about, this alpha and this beta, and they're related to each other, and there's type 1 and type 2. How are those? Just know that it's all about where you are setting the cutoff of I am willing to evaluate this likelihood. I am willing to say that this rare finding is significant or is not, and we can adjust that. But for your results section, going with 0.05 is fine. But you do need to announce this to your readers so they know what are you comfortable with saying is significant versus not significant. So 0.05 is fine. In the third step, you are going to provide the results of your analysis. This is the actual statistics. This is what we went over in the past two labs with t-tests and correlations and actually running them and providing the output and what you submitted on your lab assignment of your actual analyses. Here you will describe your hypothesis tests for your data analyses, and for each hypothesis, for each analysis you run, you need to restate your hypothesis for the reader, you need to state what statistical test you were using to test that hypothesis, and then summarize the results for that statistical test using the proper test format, again, which we have gone over. If you happen to have more than one hypothesis in your study, you need to repeat all three parts of these for each hypothesis, and they should each have their own standalone paragraph. It should be clear, one analysis per paragraph. That's the good rule of thumb. A reminder for how to report correlational results, which is from 2 labs ago, that you put it with the letter abbreviation R and then the sample size in parentheses, followed by the p-value in R squared. So you have the R there with the sample size in brackets, followed by the Pearson R value, which you compute, and SPSS will give you a p-value for you to report. Then you have the R squared. You'll hopefully remember that the R squared is pretty easy to compute, but you have to do it by hand. It is simply taking that Pearson R value and squaring it or multiplying it by itself. And so I do that by hand and put it in there. So as examples, you might find that a study was looking at the difference between stress and satisfaction. So they say there was a significant negative correlation between stress and life satisfaction or satisfaction with life, where R of 84 participants equals negative 0.25. That is a negative correlation there. The P equals 0.02 and the R squared equals 0.06. And then they provide an interpretation. Individuals with high levels of stress had significantly lower levels of life satisfaction. Good, there you go, that's it. Or maybe they were doing a study between GPA and stress and they found no relationship. So they say there was not a significant correlation between college GPA and stress, with R of 83 participants in this case equals negative 0.19. It looks negative, but we see the p-value is 0.09, which is non-significant. So no matter what that R value is, it is not significant. So we're saying there's no relationship there. And then we give the R squared, which is 0.19 times 0.19, which equals 0.04. We then indicate that we interpret that as there was no relationship between levels of stress and GPA in the current sample. So there we have an interpretation. We have all the statistics. It's telling what the variables are. All of the information we need is there and ready to go and be interpreted. For a t-test, you are going to provide the one-letter abbreviation T and then the degrees of freedom in parentheses. And you should remember that a degrees of freedom is always n minus 2, so the total sample size minus 2, because that's the number of groups that you use in a t-test. 2 different groups you're comparing, it's always minus 2. So you also have the p-value, of course, and so you have T in parentheses degrees of freedom equals the value of the T that you computed through SPSS, and then the p-value is whatever you got through SPSS. It's important to decide whether you're reporting the one-tailed or two-tailed test, and that is based on whether you think that there is a directional hypothesis or not. Choose that before you run the analysis. So as an example, here we have there was a significant gender difference, T of 54 equals 5.43, and the p-value is less than 0.001, so pretty significant, with men receiving higher scores than women. All right, cool. And maybe another alternative is there was not a significant gender differences regarding satisfaction with life, T of 86, so that means 88 participants, because minus 2, equals 0.68, P equals 0.5. That 0.5 is not significant. Remember, you need 0.05 to be significant. When you are doing these statistical tests, it's also important to remember to pay attention to italics and spacing. APA style is very specific about what you italicize, which should always be those statistical notation for mean and standard deviation, represented by M and SD, as well as whenever you're doing a t-test or an R, you have that T and R are italicized, and then your p-value, the exact letter P, is italicized. You should never italicize any numbers themselves, just the letters that signify statistical tests. You also need to round everything to 2 decimal places. I know that SPSS often gives you 3 decimal places, so you need to round it correctly. The only exception, as you saw maybe caught in a slide just before, is if you have P is less than 0.001, in which case you write out just P is less than 0.001. This is because your p-value can never be 0, and we never want to suggest it. If you rounded 0.001, you would get 0.00. We can't do that because p is never equal to 0.00. There is always a chance that we found data in our study that does not reflect the real world. There can be the probability of rejecting can't be 0. It always has to be some number. So we just say less than 0.001. So as a review, you're going to provide the summary descriptive data, such as means and standard deviations, and then the proportions or frequency for your categoricals. You're going to make sure to state the alpha level for all statistical tests, which might just be that 0.05, but wanted you to understand why we're choosing that based on the type 1 and type 2 error. And then you state what statistical test you're using and report it in APA format for each hypothesis you do. In this paper, you might just have one hypothesis, and that's fine, but you should know that in any research you read or that you do in the future, 1 paragraph per hypothesis. So here's an example of a result. So you report the mean score on the mindfulness scale was 3.8 with a standard deviation of 0.91. That's that summary of the descriptive data. Then you have the mean score on the happiness scale was 5.0, SD is 1.2. Great. You then want to announce the alpha level was set to 0.05 for all statistical tests. You're doing step 2, state the alpha level. And then finally, we have step 3, which is to do all of those elements of restating the hypothesis, stating the statistical test, and summarizing the results. Here it is. The researchers hypothesized that there would be a positive association between happiness and mindfulness. A Pearson correlation was run to test this hypothesis. Happiness and mindfulness showed a strong significant correlation of R of 148 participants equals 0.42. The p-value equals 0.02 and the R squared is 0.18. This indicates that as happiness increases, mindfulness increases. There's your interpretation. And then we interpret the R squared as well. 18% of the variance in happiness was explained by mindfulness. Great. We have all of the pieces we need to report that correlational study. If you have questions about how to report, there are examples in past labs. You should also be looking at other research as you're collecting to see how they report. All of the information is there. If you have any questions about it, make sure to reach out to your TAs. They know how to write up results section. So if you're unsure if you've included all the elements you should, just go to them. Note, if you ran a t-test, you would also have to put the t of degrees freedom, the value of t, p-value, etc. Also, for a t-test, you want to include the group means and standard deviations. Correlation doesn't have those because you don't really have there's no categories, but you do need to have those subgroup means and standard deviations indicated there. All right, so as a checklist, again, I said talk to your TAs, but here you go, at least you have something. What are the means and standard deviations for continuous variables that you analyze? Make sure to have those. You also want to have the proportions, and if you have groups, you need to have the means and standard deviations within those groups. What was the alpha level? Make sure that that's there and clear. What was the hypothesis that you were using that you're testing right now? And you're reporting your research hypothesis. You don't have to talk about null hypotheses and alternative hypotheses. Just take it from your introduction. What do you think is really happening in the real world? You then have to describe what test did you use. Make sure you say whether it's a correlation or an independent samples t-test. And then make sure you're reporting the results of your test consistent with APA style. The last part that a lot of people forget about, they think they're done when they get those data and those numbers down. You always need to have a short statement of what the results mean in simple terms. You should also tell what the R squared means and what does the t-test mean. This is an interpretation. You are not talking about the implications of what you found. What does it mean for the real world or anything? You're simply saying, what does that in normal terms, explaining it to your grandmother, what does the results of your analysis say about how the variables are related to each other? That's it. All right, that's it for today. So I am going to be posting on Canvas a results section worksheet. This is just guidelines of all of those things I just described that you need to include for your correlation or t-test to fill out. This is not an assignment itself, but it is very helpful. And as you fill it out, if you're unsure whether you've included all the information you need to, this is a great chance to reach out to your TAs for feedback. You can reach out, share it, and say, hey, does this look right? Is there anything that you think is missing? Did I interpret correctly? Did I find that line between talking about what it means without going into implications? That is for you to reach out. So you need to take the initiative yourself to talk to your TAs, to show up to their office hours and get that feedback, because you will be submitting your results section in your final that's the version you're sending. So you want to make sure it's right. Next week, we're going to start talking about the discussion section, and we're going to have lab assignment number 6, which is a discussion section worksheet. I'll be posting this a little bit ahead of time, so you can start looking at it now. But next week, we'll really talk about what does the discussion need in it? What are all of those questions that I'm asking in the discussion section worksheet? The worksheet will be formulated such that it's more filling out just paragraphs. writing kind of your answer to individual items, but then in your actual discussion for the paper, you'll have to synergize all that information into a prose, into the format that your final paper is presented in. So take a look at that now, and again, be reaching out to your TAs regularly. This is especially a time when you want to take advantage of their support. That's what they're here for, to make sure that you're as prepared as possible for that final paper. All right, that's it. Have a great one. Talk to you again.